All right, so now we're going to look at a problem from section 23D. In 23D is an application of the derivative rules that you learned in chapter 23, namely being logarithmic functions, finding the derivatives of those, and exponential functions, finding their derivatives as well. So let's go ahead and dive into problem number 10 shown here. And once we get to the piece of actually finding a derivative, we'll see how we go about applying that particular derivative rule. All right, so we have that the temperature of a liquid after being placed in a refrigerator is given by T equals 5 plus 95 e to the negative kt degrees Celsius, where k is a positive constant and t is a time in minutes. So we need to find K if the temperature of the liquid is 20 degrees Celsius after 15 minutes. Then they want us to find the temperature of the liquid when it's first placed into the refrigerator. Then once we get to part C, that's where they want us to take a derivative and show in this case that it's directly proportional to our original function minus 5. Then for part D, they want us to look at the rate of change for the temperature at time equals 0, time equals 10, and time equals 20. So let's go ahead and get started with part A, finding K. And once we find K, we'll be able to use that for the rest of these sections, or each of these parts, B, C, and D. So for A, we're looking for the value of K, our positive constant, which means if we get a negative, something's wrong. And it's for when T, our temperature, is 20, and our time, it's after 15 minutes, so T equals 15, little t. So to find K, we're simply going to use this equation that we have for temperature, plug in the values for temperature and time, and solve for K. Not so bad. So that means I have 20 equals 5 plus 95 e to the negative k, and instead of t, I put 15. And now we're looking at a problem similar to what we saw in 23b, where you're solving for a constant that's either hanging out with a natural log or an exponent. So let's go to work. So first I'm going to subtract 5 from both sides, and that gives me 15 equals 95 e to the negative 15k. Then I need to get rid of this 95. To do that, I divide on both sides. So I have 15 over 95 equals e to the negative 15k. And then I have an e. So now I need to figure out a way to take out that exponential. Well, from the sections that we looked at earlier, we found that if we take the ln of both sides, that'll take care of the e. It'll cancel it out, and we'll be simply left with the exponent, in this case at negative 15k. So now I have ln of 15 over 95 equals, again, ln and e cancel out. So then I've got negative 15k. And for our final step, to get k by itself, to solve for k, we divide both sides by negative 15. So I have ln of 15 over 95, and then all of that is over negative 15. So when I put this into my calculator, I am getting, let's see here, yes, I'm getting approximately 0.123. So 123 thousandths, or 0.123. And this is the value of k that we are going to use for parts B, C, and D. Just to keep it handy, I'm going to write it up here next to part A. So k is approximately equal to 0.123. All right. Now as we go into section B, we need to figure out the temperature of our liquid when it was first placed in the refrigerator. Right. Part B. Well, we are looking for temperature, so that means we're looking for our big T. And when it was first placed in the refrigerator, reads a little bit like initial. Remember the initial problems from chapter 22? And when we had those, we knew that told us that our time was 0. It's the same case here. So now I have my time and I have K from part A, and I can use that in my function for my temperature to figure out the temperature at time equals 0. So at time equals 0, looking for my temperature, I'm going to have 5 plus 95 e raised to the negative 0.123. That negative was there from before, so K itself is still technically positive, and my T value is 0 for my time. So let's go ahead and work out this pretty straightforward evaluation. So I've got a negative number times 0. Well, anything times 0 is going to be 0, so that goes out. And if I rewrite that here, I've got 5 plus 95 e to the 0. Well, anytime I see e raised to the 0th power, or anything raised to the 0th power, automatically a 1. So that means I have 95 times 1. So I'm dealing with 5 plus 95, and that gives me a nice round 100 degrees Celsius. So that's the temperature of our liquid when it was first placed in the refrigerator. We can use that and write it again on this top space. So I've got that my temperature at time equals 0 is 100 degrees Celsius. Okay. Now we get into part D. Or sorry, not part D, part C. Oops, skipping ahead. So when we're looking at part C, that's where they're wanting us to find dt over dt, or the derivative of our temperature with respect to time. And they want us to show that it's directly proportional, meaning that we're multiplying by some constant value, some coefficient, and it's that value times our original function t minus 5. So let's go ahead and find our derivative. So we're looking at, this is C, our original function of temperature with respect to time is 5 plus 95 e to the negative 0.13 t. Now from what we learned in part, I believe that was part C, if I'm not mistaken. No, just kidding, it was part A. Haha! In part A, we learned that when you're taking the derivative of an exponential function, it's actually very clean and straightforward. You're going to take this same e to your original. You're going to keep that. And you're going to multiply to it your derivative. Just like that. So you have your e to raised to whatever. That's what you're going to keep and place here. It's part of your derivative. And then you're going to take the derivative of this original function. So just to make sure it's not looking too confusing, if you were to take the derivative of e to the, let's go with pi x, just to give something that looks slightly nasty that really isn't. Okay? When you take its derivative, you would still have e to your original. In this case, your original is that pi x. So I still have e to the pi x. And then I multiply to it the derivative of this original. So the derivative of my pi x. And the derivative of pi x is, just simply pi. And that is my derivative. I am done. Not a problem. So we're going to use that same set of logic over here when we're dealing with this e to the negative 0.123t. When we take its derivative, we're going to still have e to this raised exponent, but then we're going to take the derivative of the exponent and multiply that. So let's go ahead and get started. So when I take the derivative of 5, of course, is just simply 0, so I'm not going to worry about putting it. Then I have 95e to this negative 0.1.23t. So I'm going to keep the 95 part still separate. And then I've got my original, just like we had over here, e to the original, so e to the negative 0.123t. And then I multiply to it the derivative of negative 0.1.123t, which is negative 123 thousandths. Sometimes it's easier for me to say. All right, so that is our derivative. Great. Now we need to show that it's directly proportional to t, our temperature function, minus 5. So let's look at what t minus 5 is. If I do t minus 5, means I have my t, which is at 5 plus 95 e to the negative 123 thousandths times t. And then I'm going to subtract 5 from it. Well, I have positive 5, negative 5. Those cancel out, and I'm left with 95 e to the, negative 0.123 t. Wait a minute, that looks just like this, doesn't it? Just like what we saw in our derivative function. Aha! And the only difference is this negative 123 thousandths. Ha, said it. And this is going to be essentially our coefficient or our constant that creates that directly proportional relationship. Super. So we're able to show that that is true. And in fact, we're going to put that off to the side. I'm going to write that up here. We can say that our derivative, meaning our rate of change in temperature with respect to time, is the same as negative 0.123 times, we can actually replace out, instead of saying this 95 e to the negative 123 thousandths times t, and just put t minus 5, because remember, it's all equal, right? So we can say that it's equal to that over here, t minus 5. Super. So now, when we go into part D, we actually have a few options on how we can answer those 3 parts for the different times. And in fact, this is a fun little calculator exercise if you'd like, in that we have 2 methods. Our first method is to say, all right, I found out what the derivative of t was, and using that, I'm going to just simply plug in my times and be done. You give me time, I can tell you the rate at which the temperature is changing at that time. Straightforward. The other option you have is to say, wait a minute, I remember that in part C, we found a relationship between the derivative and my actual temperature at that time. So I could find T first, so this isn't the derivative, this is the temperature at that time, find that first, and then plug in to that derivative of temperature. Okay, so then we'd plug into, let me put that there, plug into, okay? Either way you do it, you'll still be able to find the rate at which your temperature is changing for those 3 times. If you have some lingering questions still though on setting up part D, not a worry. Just send me a text, or you can call or email me and I'll be sure to help you out to make sure you've got these derivatives taken care of. Again, exponential and logarithmic functions, really not so bad. Until next time, take care. Bye.